I am Molly Resch, and last spring I worked on synthesizing a bismuth nanoparticle to conjugate it to a chemotherapeutic agent under the supervision of Drs. Kenneth Reed and Gary Skuse. Why synthesize a bismuth nanoparticle? Well, for a start, it's inert, both in the human body and to our chemotherapeutic agent. Second, it's diamagnetic, which means it has the potential to be magnetically steered through the body to a tumor and then magnetically steered back out of a site where the chemotherapeutic agent can be removed. Additionally, it is a 2 to 5 nanometer vehicle or Trojan horse for our dye or chemotherapeutic agent package, which means that it can translocate across the blood-brain barrier for the treatment of brain cancer, an orphan disease. Our chemotherapeutic agent is a cyanine dye that comes from Kodak's photographic process. It has terminal benzothiazole moieties, and its backbone is a thiazole. It kills cancer cells with high selectivity, meaning that for every 900 cancer cells it kills 1 healthy cell. For comparison, adriamycin, a commercial chemotherapeutic agent, kills 2 cancer cells for every healthy cell. We believe that this dye has this ability because it is a small molecule mimetic of a protein in the BCL2 family, which regulates apoptosis. This is our target product, with our dye conjugated to our nanoparticle. It is a scale representation, and it is courtesy of Dr. Alistair Cormack from Alfred University. However, our chemotherapeutic agent has some problems. For a start, when it was tested in mice, it killed the mouse tumors, but when trying to leave the body, it formed J and H aggregates in the liver, and aggregated in the liver, causing the mice to die, which was an extremely unfortunate unintended consequence. Additionally, it has 8 geometric isomers, and we don't know which ones have been used in previous testing of the dye, so we don't know which one is the highly selective chemotherapeutic agent. Finally, it has limited solubility and is only known to be soluble in lactic acid. This meant that it was important to choose the right reagents, starting with our bismuth species. I considered the oxide, the nitrate, the hydroxide, and the acetate, and all of them were largely insoluble in water. But bismuth hydroxide was the most soluble in water, so that's what I chose to be my bismuth species. Then it was time to look at the nanoparticle stabilizer. Between lactic acid and EDTA, lactic acid was already involved in our process since it solubilized the dye, so I chose lactic acid. When considering reducing agents, I looked at hydrazine, citric acid, and ascorbic acid. Of the 3, hydrazine has the highest reduction potential, and its reduction potential increases with pH, which means it works very well with bismuth hydroxide, which is a base. All of these come together to form our target bismuth nanoparticle. This image was once again courtesy of Dr. Alistair Cormack of Alfred University. Since bismuth hydroxide is largely insoluble in water, we needed to find another solvent. The difference in electronegativity between bismuth and oxygen is 1.42, which is less than the 1.7 needed to be a completely ionic compound. This means that bismuth hydroxide has both ionic character and covalent character, which caused us to think that perhaps an ionic solvent could be the answer. An ionic solvent contains both a liquid acidic component and a liquid basic component. They come together to form a single phase and a single solvent. For my ionic solvent, I chose lactic acid as the acidic component and hydrazine as the basic component. They work well together both in the context of our project and because they both experience hydrogen bonding. Once I had selected my ionic solvent, it was time to test it. I created 8 solutions of lactic acid and hydrazine, and they were all of differing pHs to see if any would dissolve bismuth hydroxide. The pH ranged from 2.02 to 11.14, and after I mixed together my hydrazine and lactic acid, I added 1% bismuth hydroxide by mass to each solution. Unfortunately, bismuth hydroxide was not soluble at any pH at room temperature, so I put it in a heat bath for roughly 2 days to see if that would cause the bismuth hydroxide to dissolve. and it did in samples with pHs from 2.92 to 8.97. In samples with pHs from 9.97 to 11.14, it dissolved the bismuth hydroxide, reacted with the bismuth hydroxide, and precipitated out bismuth clumps. This showed me that lactic acid was not a good enough stabilizer for the dye, or for the nanoparticle thermodynamically, but it remained important to our conjugation process. So I tried another experiment using lactic acid and slow heating in a heat bath. As you can see, I did not get very promising particle sizes, since all of these are in the microns. I found these particle sizes using a Malvern zetasizer, which utilizes photon correlation spectroscopy and dynamic light scattering to measure particle size. Since slow heating in lactic acid wasn't working, I decided to switch to fast heating in a microwave and EDTA, or ethylene diamine tetraacetic acid. So I changed the acidic component of my ionic solvent to EDTA, and then I mixed together EDTA and hydrazine to create solvents that had pHs that range from 10.25 to 12.63. After that, I added 1% bismuth hydroxide by mass, and then I put each scintillation vial in the microwave for 10 seconds at full power. I was able to take particle sizes for every sample except for 3, which evaporated in the zetasizer. During this experiment, in my vial that had a pH of 12.63, I was able to create particles that had a size of 535.8 nanometers. This was very promising and showed me that using EDTA and fast heating in a microwave were very important to creating a nanoparticle. However, the particles I had created, the smallest particles I had created, were still roughly 100 times too big for the project I needed to complete. So it was time to add something a little extra. I put all of these chemicals had the ability to stabilize bismuth nanoparticles. So I tried adding them to my solutions after heating. I made up 6 solutions using the same recipe I used to make the solution at pH 12.63, and then after heating I added each of these to it to see if any of them would be reduced favorably by hydrazine and if any would create smaller nanoparticles than I had already created. I found out that of the 6 quenching agents, benzothiazole was the only one that was reduced by hydrazine, and it produced a yellow solution instead of the black one I expected, so I knew I had not made what I wanted. Of the rest of them, orthophenylene diamine stabilized the bismuth particles the most. It created 788.1 nanometer particles, and because of that result, I decided to retry my experiment using orthophenylene diamine and a fifth of the amount of EDTA and hydrazine. When I did this, I created particles that were 2,547 nanometers in size, which was much larger than I wanted, leading me to believe that perhaps I should add stabilizer before heating so that each vial spends the same amount of time with stabilizer in it. Because of the COVID-19 pandemic, I was unable to continue my research, but based on what I've seen, this is a summary of my current thoughts. First, ionic solvents appear useful for our process, since it is very easy to control their pH. Additionally, hydrazine and lactic acid are both good for my nanoparticle separately, individually, but together they don't work well to create small enough nanoparticles. Third, the thermal conversion of bismuth 3+ to neutral bismuth is best done rapidly in a microwave, like I have been doing. Fourth, an adjuvant stabilizer may be necessary in the initial stages of the reduction in order to make small enough bismuth nanoparticles, since thermal and chemical quenching did not seem to work that well. And finally, adjuvant stabilizers might be best thought of as linking groups from the dye to the nanoparticle, where one end of the solvent stabilizes the nanoparticle and the other end solubilizes the dye. In the future, I'd like to repeat my first experiment solubilizing bismuth because I did not take particle size during that experiment, and I would like to retry it to see if there was anything I missed. Additionally, I'd like to retry my experiment with the stabilizers, this time adding my chemical quenching agents at time equals 0, like I mentioned before. And finally, I am considering looking at metal oxides such as superparamagnetic iron oxide nanoparticles, or spions. Spions would work magnetically oppositely to bismuth nanoparticles, but they may have other effects that bismuth nanoparticles don't have that are good for our dye. Additionally, they have already been created. The research on spions has been done by Carly Augustin, Lizzie Kane, and Madeline Swade. Finally, I'd like to thank my fellow students, Emily Wrightstone, Corey Cornewick, and Jeremy Kane. Thank you.